My name is Sabbagh, and my presentation is on the mechanical testing of the subtalar implant. In this presentation, I'm going to talk about a brief introduction about what the subtalar joint is, the purpose or need for research, my role in this project, so the project objective, the design of our experimental setup, the obstacles we encountered, and a brief summary of what we attained. So the subtalar joint. The subtalar joint is a joint within the hind foot, and it's located between the talus and calcaneus bones. It's responsible for the inversion, eversion, or side-to-side movement in the foot. Like any other joint in the body, it can experience wear with age or osteoarthritis or any sports injury. The common standard treatment is bone fusion of the talus and calcaneus bones. So although this alleviates discomfort and pain, this still limits the movement of the joint. So some implants have been created, but no testing is currently being done. So our purpose, need for research, is to actually test the subtalar implants to see what their efficacy actually is. So the testing device would mimic the movement and loading experienced by a subtalar joint, the loading being the body weight of the person, and the rotational displacement being the movement, the inversion, eversion movement. So project objective. My role in this project has been the experimental setup of this testing apparatus. This includes two components: the mechanical installation of all the components into the existing axial testing device, and also the electrical wiring of the motor and electrical parts. So the design of the experiment. Our experiment required several parameters to be designed, and since no testing standards currently exist, we decided to base those on the hip joint standards. So we decided on 50 to 800 newtons as cyclic loading to be applied axially at 10 hertz, and the rotation to be between 10 and negative 10 degrees, and this would mimic the inversion eversion movement. So our implants would be tested within a water bath containing bovine serum solution diluted in deionized water, and we would assess the implant wear by inspection and also by gravimetric means. So this means measuring the actual content of the solution. So the design of the rotation, we designed a 4-bar crank rocker system that, as you can see in the video there, as the red linkage rotates a full cycle like a motor would, the blue linkage rotates through a specified rotation, and that would be the inversion eversion movement. So the electrical components, because our loading would go through 50 to 800 newtons, and then 50 and 800 newtons, and then 50 again. So for that one cycle, we only have half a cycle of rotation. So therefore, our motor needed to rotate at half the frequency of our loading. So for this purpose, we used a variable frequency drive, or a VFD. So our mechanical components, onto our axial testing machine, we added 2 steel plates. It's not very clear in this picture, but one steel plate at the very top contains the water bath and the ball bearing and shaft coupling system, and then another steel plate at the very bottom would carry the motor. So experimental setup. We start with our axial loading machine. We add our top steel plate, and then on top of that we add the water bath. And within the water bath, all the other components would go. This includes the 2 bearing blocks, the bearings, shaft, and then you can see here there's a blue printed block, and this would be where the implant would actually go. And we have the water bath gate to hold the water within it. And then we have the electrical setup of the VFD. So the VFD is actually a single phase VFD. So this means it can be plugged into a regular power outlet. And so that can be seen on the left side here. And on the right side, we have wires connecting to the 3-phase motor, and there's 4 wires for this, 3 for the actual motor and 1 grounding wire. And here's just an image showing the wiring of the motor. I'll talk about why this is important in 3-phase and single-phase in a few slides. So the mechanical setup of the motor, we took our motor and we installed a bushing in the very end to sit flush against the shaft. So this would allow for the attachment of the linkage on it, and that would essentially rotate the coupling system. So the motor is mounted onto a motor plate. This plate seen here, picture to the left, it's mounted on top of the entire system. And then the motor is held in place by four bolts, 4 washers, and 4 nuts. So having that initial coupling system at the top and the motor at the bottom, we attach a 3D printed piece, which I'll talk about very briefly. So this 3D printed linkage is then connected to the motor using a longer metallic linkage. And then I'll talk about the obstacles encountered. But at this point, the entire setup is essentially complete. So the obstacles encountered. The very first obstacle is I'm actually a civil engineer with a civil engineering background, and I know nothing about electrical engineering. So we had to spend very many hours researching the internet and sifting through a lot of useless information before finding what we actually needed to know. One obstacle we have with a 3-phase motor is that a 3-phase motor needs to be supplied by 3-phase power. So in order to run that, we needed to find a way to run it. We only had one 3-phase outlet in our biomechanics lab, but that was running our axial testing machine. And we found the VFD we bought is able to control and power the motor. So our VFD can just be connected to any power outlet, like any one you have in your house. Some obstacles we had weren't really things we had foreseen before, and this just happens because in construction, a lot of things don't go as planned. One thing we had was a lot of the threads were damaged. In the picture on the left, you can see the threads at the very bottom are very nice and smooth, whereas the other threads at the top right are very obviously damaged, and you can see the poor fit of the bolts in the right edge. So we had to get that rethreaded. Another obstacle we had is that the water bath bolts did not align with the steel plate. So we actually came up with a solution to use smaller bolts to not thread through the steel plate, but instead to be nutted at the very end, and this would provide the compression necessary for the face seal. But another issue came up with that, where the mortar plate would interfere with those water bath bolts, so we couldn't have them there. Proposed solution is to use C-clamps to provide the compression, or to drill holes within the mortar plate to have room for those water bath bolts. So another obstacle we had was that a drain plug is necessary for the water bath to release the fluids. And for the water to go through down to the drain, it has to go through the top steel plate, it has to go through the original steel plate, and then it reaches the drain. And then within the 2 steel plate interfaces, there is a small gap for leakage. So we fitted that with a rubber tube to prevent the leakage. So another obstacle we had was that the bearing block we received from the manufacturer was way too short. So a temporary solution for that is to use washers for a demonstration until we get the block actually replaced. Another issue we had overlooked is when you drill holes, you drill threads into multiple steel components, you have to have them drilled at the very same time. Otherwise, the threads will not align. And that's something we saw very quickly in multiple things. It happened in the bearing blocks shown on the left, and then again in the 2 steel plates that connect to each other on the right. And the solution for this is to drill a through hole in the very top plates, or in the left, the bearing blocks, and then to only keep the threads in the very bottom. And then the compression and the bolt would keep the 2 things together. So another obstacle we had was an easy fix, and this was just the holes for the bearings and the linkages were misshapen, so we had to reshape the holes to be perfectly circular. Another linkage obstacle is that the linkage itself was actually loose on the motor, and there's a small video showing this. Should be right with this. But anyway, the video would show basically the linkage hitting the motor as it spins. And the solution for this was to use a shoulder screw with a shorter barrel. And this is something, even though in design it should work, it's something that's modified in construction. So the mechanical setup of the linkage, the short linkage, we had initially designed it to be connected directly to the shaft, as you can see in the small hole on the very left. And we had our coupler and our short linkage to be separate components. But we modified the design to have them connected together via welding, and this would allow for a more secure fit. We couldn't get this in time for the demonstration, but we 3D printed a component to actually try it out. So we couldn't get an actual implant in time, so we had to 3D print an implant for this. the test, and I'll just show a video demonstration real quick. Just playing.
It's on YouTube.
Okay, YouTube.
Yeah. This is the
No,
last
I
thing,
don't think
right?
it's hooked up to the internet.
It's not really. It is.
I don't think it is.
Okay, if I connect internet. Is there time?
This is the last thing?
It's the last thing. isn't it?
Yeah, go ahead.
I just really want to show it. It's all the pictures don't mean anything if you can't see it move.
It's okay, Joseph. We trust it's working. So.
It's open. It's open. You can see as the motor spins, the long linkage moves up and down, and that spins the entire coupling system. And while this happens, we have an axial loading applied. And that is essentially it. Does anybody have any questions?
This is the last presentation, so if you have questions for
That's
Joseph.
quite impressive.
So I just wanted to ask if you were going to have that, what did you call it? Those two parts oscillating, right?
Linkages.
What?
The linkages?
The linkages, yes, If you have that oscillating. You want to apply an axial load on
Yes.
top of that, right? So is it like supposed to be displacement controlled or load controlled?
I'm sorry, I can't hear you.
Your experiment, will it be displacement controlled? I mean, for applying the axial load, because I'm thinking if you're going to apply the axial load, are you applying it gradually? Are you applying a displacement
Yes.
to that and then measuring the load, or are you just applying a certain amount of load?
We're applying a cyclical load, so it varies between 50 newtons to 800 newtons.
So you're going to be applying different loadings and then checking.
It varies as it rotates. So the very neutral position at 0 degrees, we have 50 newtons, and then when you reach the two extreme points, 10 degrees on either side, you would hit 800 newtons.
Okay.
Does that answer your question?
It's displacement control, the rotation, load control, and the load.
Okay, so you just keep changing the load, and they change it, make it 50, do that, make it 100 too. Oh, okay.
Does anybody have any other questions?
Any other questions for Joseph?
Thank you.
Thank you again. And give yourself a round of applause for all of you.